Hi everybody, this is a first video to bring some companion material to the post that we provide in the First Practica blog. And the topic of today is single points of failures, SPOF, sometimes abbreviated. We've seen that computing has dealt with single points of failure for decades. In fact, computing mirrors life. And life, if you look at the body, we've got two lungs, we've got multiple cells, multiple veins, arteries, we have multiple pathways. And you look at nature and you realize that nature has architected itself over a very long time as redundant. Redundant meaning robust, and being able to sustain the loss of part of the system and to be able to recover from that. And these redundant pathways, the fact that we are distributed, the species are distributed, the loss of one individual or even one species up to a point does not affect the entire system. It does not collapse the entire system. So computing has looked at this problem, and it has faced this problem of the single point of failure for a long time. If you look at the few pieces, the main pieces of a computing system, it starts on the right. It starts where data is stored. Think about a hard disk. If we lose the hard disk and it's the only place where there is data, that's a problem. And a database is basically a store that can fail. And this has been very studied. There have been many ways of architecting redundant databases by doing clusters, by doing failover, standby servers, by replicating data off-site to different locations, so that when data becomes very important, and the more important data becomes, the more that database has to be somewhat copied elsewhere and resist the loss of the compute power on that database, potentially data corruption around that database, ways to access the data. Anything that can impact that has to be basically backed up, and we can restore it fast. The same goes for the compute instances. And the cloud, whether it's Amazon or Google, the cloud has become very good at being able to make those compute instances robust by failing without consequences. And typically that's done by doing backups, of course, and then stateless server architecture, which is that what is in the instance can be erased, it can be lost, and the data and the files in particular, outside the data, the files in particular are stored elsewhere. And so there's redundant paths to compute instances, and that's mostly done by, continuing on the left, by load balancers. Load balancers are interesting because sometimes they fail, and there's not always a good mechanism to actually cope with a loss or errors in load balancers. So databases, very mature, compute instances, very mature, load balancers, good but question mark. Continuing on towards the edge of the network, content delivery networks provide a copy of static assets. So if a page is static, it can be cached fully, including images, video materials, everything that is static can be cached on the edge of the network. And if it's fully cached, it never hits the database. It never hits the compute instance. Everything is served out of the cache. So that provides a great redundant path in the event the backend servers are not available. The cache itself can fail, because if it fails, then what it means is that the cache is not there, so it's going to go to the load balancer, it's going to ask for the data, and it's going to serve it back. So to some extent, the loss of cache is not a big deal, because it can go back to the origin, provided that the origin is alive and it's accessible. And then last month, many sites went down. Twitter went down. Who else? GitHub. Many sites went down for several hours. And when these sites are so big, one would think that they've architected their system to minimize the downtime, and it was quite long. What happened is that the DNS provider then got DDoSed, which is essentially lots of requests sent to the DNS provider, overwhelming the DNS provider, and then basically that part of the network is dead. That part was a single point of failure because they could not reroute the DNS fast enough to minimize the downtime. And that's basically the subject of this post, which is you look at the chain that serves websites, web applications, and you can see on the right that so much work has been done on the compute instances, so much work has been done on the databases, that there are ways to lose part of that service and recover somewhat fast. But to the end, to the left, we saw recently that this is not the case. So DDoS is a complex problem. It hit DNS providers, and DDoS can hit any place. So of course DNS has to do its own change. It has to figure out a way to, like databases, provide redundant paths to customers and to users, so that if the DNS servers melt down from a DDoS, there's a way to quickly reroute traffic and reconfigure so that the sites become available again. The second part that we talked about in this blog post is the fact that DDoS attacks have a profile. It's a lot of requests that's unusual to a particular domain name, particular IP address, particular endpoint, and you would think that there are rules that can be written at the network level such that if something unusual like this happens, they have to be shut down before they hit the site. And this has not happened yet, and it's perhaps another way to mitigate and to solve DDoS attacks, DNS failures, single points of failures where at some point the network is going to overwhelm the resources available, even if they're backed up. So that's it. Thanks for listening. Talk to you soon.